For the introduction, so I'm Bernd. This is work on breaking parsers. This joint work with Mukherjee, who gave the talk in the morning, and Jan Taljat, who is also an MSc student at Stellenbosch. What are we doing? We're breaking parsers. We're doing testing. We're doing grammar-based testing, right? So the idea of grammar-based testing is you have a two-phase approach. In the first phase, you're generating your test suite. Typically, you run some sentence generation algorithm over your grammar. So here we have a small grammar. We run some kind of sentence generation over this that guarantees rule or CDRC coverage or whatever you want to do. That gives us a test suite, a set of words that are a set of strings of tokens, I should say, that are actual words in the language, right? And the second phase, we take this test suite and run our unit over, or a unit under test over this, right? So we have whatever, GNU-ADA or some kind of compiler, and we execute this on each element in our test suite. And the output is either pass or fail, right? The compiler says yay or it says nay. Right, that looks fine. Now let's look at the outcomes. If one of the tests fails, we know that the unit under test is not correct with respect to the grammar, right? Because it accepts a word, because it's just not in the right language. But what we want is when everything parses, we want to claim that the unit under test is correct, that the languages are equal. Of course, that's not the case, right? For instance, we can replace our other compiler by something that just says echo OK, right? That unit under test can never fail on a test suite that contains only positive words if the language implemented is a proper superset of the grammar of the language of the original grammar. Right? So if you always say yes, we're always on the safe side. Right, so that is one of the problems of grammar-based testing, and that shows up in reality. There were questions like earlier in the talk, right? So if we only have positive test cases, then we fail to find many kinds of errors. For instance, if we have in our grammar, in the unit under test, optional elements that shouldn't be optional, right? If the priority clause is optional, but it should be given. If we generate test cases from that grammar, it will always have the priority clause, and we will never find out that our unit under test also eats up programs that doesn't have it, right? Or if our unit under test allows declaration or lists of declarations, or if it has alternatives that are not in there, if it allows another type, for instance, or if it overgeneralizes some of the symbols, right? If it allows an expression at the priority rather than just a numeric literal, or if it is not so fussy about the order, declarations and statement can be mixed. Our grammar that we use to generate the test suite always has the declarations before the statements, because that's what the grammar says, right? But our parser will eat up everything. We never ask it to eat something wrong, so we never find out. So the point is that we really need negative tests to find out false positives, right? So what's a negative test? Well, that's just a word that's not in the grammar, a sequence of tokens that's not in the grammar, something that is guaranteed to produce a syntax error, and the unit under test must reject it. Right? There's a few problems, though. So we need to make sure that we prevent accidental derivations. So, right, this is a, hopefully, C program, right? And we could say, look, we just change this thing and make it syntactically illegal. So, for instance, we just remove the else. Unfortunately, that is still a valid C program. Rather than if and else, it's now two statements. Or if we have an assignment that has on the right-hand side a function call, and we break that function call by inserting a plus between f and bracket, it is still an expression. Right? So when we try to generate negative test cases, we must make sure that there is no accidental derivation from other parts of the grammar that legally eat up that input. Right? Another problem is that we really want concise test cases. So for those people who go recreationally slumming at software engineering conferences, fuzzing is all the rage there, right? A simple fuzzing approach doesn't work. We cannot just, well, we can, but it makes no sense to just spout out a sequence of tokens because we don't really cover the error space, right? It will almost certainly break at the same first token. So we want to be better than that. We also want test cases that are as small as possible. For instance, here's a program that's illegal in the grammar that we've seen before. The identifier is missing, but it's in some sense too complicated. There's the entire declaration that's not required. It's after the error. We want test cases that are very concise and pinpoint the location where the error in the grammar is. You can see where this is going. And we want, if possible, a single well-defined error. Right? If we have this assignment or this conditional in our language, well, it's not legal, we know that, but what is the error? So if it was because there was a plus that's missing, then this becomes an expression and the entire thing becomes legal. If we delete the identifier, this is also an expression and the entire thing becomes legal. Or if we insert an else in between, then this entire thing becomes an if then else and it becomes legal again. So figuring out what the error is isn't quite that simple. So this is where we're going. We are trying, or we've defined a way of generating programs that are guaranteed not to parse with the grammar that's being given. And we do this by fuzzing, but not by simple, straightforward fuzzing. We're doing a mutation-based language fuzzing approach. Right? So here's the idea, or here's the key observation that underlies this idea. If we have a sequence of tokens, and we have two tokens, A and B isn't in the follow set of A, then this thing can't be a legal word. Right? Very easy. If it were a legal word, then B must be able to follow A. If it can't follow, it can't be a legal word. And that's what we're going to exploit. We just use this. We can now define locations at which we apply string edit operations, the standard string edit operations that is used, for instance, in div, to fuzz an existing positive test suite into a negative test suite. So we use, for instance, rule coverage to generate a positive test suite, and then we fuzz all locations in specific ways so that this is guaranteed to be satisfied, and that guarantees us that that fuzzed test suite is negative. Every fuzzed word has a syntax error. And the third idea is that we can do this not only at the level of characters, starting with a positive test suite, we can do this directly at the level of the grammar rules and then generate negative test cases directly. Right, so let's look at the first simple basic notation. Just to make it shorter, I call xy a poison pair or a poison pill if y cannot follow x, or alternatively, x cannot precede y. So that's the idea that two tokens cannot be next to each other. And that's the core technical idea here, right? We use that now to define word mutation operators. And these are the standard string edit distance operators with preconditions, right? So if we have a string with ABC in the middle, and we know that AC is a poison pair, then we can delete B, and the remainder is guaranteed to be illegal, contain a syntax error. Right? That's just lifting the standard delete operation from string editing to the level of grammars. Right? We can define this also for token insertion. If we know that AD is a poison pair or DC is a poison pair, then we can insert D between A and C, and we've constructed a program with a syntax error. Right? And we can do this for the other string edit operation like substitution and transposition as well. And we've got to be careful. We cannot chain these operations, right? We cannot guarantee that if we apply two of these mutations that the outcome is illegal. Obviously, if we insert something and then delete it again, we're back to where we are, and clearly that was a legal word. If it was a legal word before, it's a legal word afterwards. Right. So how do we do this? The algorithm is really, really simple. We start off with a positive test case. Here's an example. And then we run over each word in our test suite. We run over each position in our word and over each operator from our operator family. If its precondition is satisfied, so if the Poisson paired relations that I've shown there are satisfied, then we just apply that mutation and print out that thing. And that gives us a negative test suite. Right? So here is a subset of the negative test cases that are derived from this one positive test case. For instance, we delete every single token that we know leads to a syntax error. Right? Or we replace the equals by every other token. Now, this does not always get us a syntax error, right? For instance, if we replace that equals by then it's not guaranteed that this is a syntax error, right? Because the context at which we are checking is just the immediate neighborhood, just the Poisson pairs, right? If we go further down and if we insert then before the L for the equals, then we get the Poisson pair relation, right? So then can follow Y, but it cannot precede equals. So that's why we know, that's how we know that this is guaranteed to be a syntactically incorrect program. Right. So that's the first thing. We've just taken a positive test suite and fuzzed it with string edit operations. That gives us kind of shallow test cases. In the second step, we're going to lift this from the level of tokens to the level of symbols in a grammar. Right. For that, we need a slightly extended notation. We're going to define a left and a right set. So the left set is the set of terminals that can occur to the left of the designated position in an item corresponding to a rule. Right, so we have the rule A goes to alpha beta. We have the designated position between alpha and beta. And the left set is all the tokens that can show up right to the left of this bullet. Right? So it's the last of alpha if alpha is not nullable. Otherwise, is the union of last of alpha and precede A, restricted to the token sets. And the same for right. We can use these two definitions now to lift the conditions from tokens to rules. Right. Let's look at an example. Right. So the symbol deletion. Let's assume we have a rule, A goes to alpha, x beta, and we want to delete x after the designated position. We are allowed to do this if the follow set of the left set of that resulting item is disjoint from the right set of that disjoint of that item, or the other way around, if the left set is disjoint from the precede of the right set. If that is the case, then any derivation that uses this modified rule leads to a word that is not in the language of the original grammar. So what's the intuition here? We have this derivation going from as in the grammar to gamma A delta. And then we are applying this modified rule, A goes to alpha beta delta. Right? So the idea is that we take the yield of alpha, and then whatever can precede alpha, and whatever can follow that set of terminals. Right? So that's the follow set of this. Right? So that's left and follow. And if that is disjoint from whatever can be constructed on the other side, if these two are disjoint, then we know that we have a Poisson pair in any possible instantiation of alpha and beta. Right? So that's the idea. We can lift this, we can use this to define conditions on all of the other operators, for instance, symbol insertion, or transposition or replacement. Right. So that's a relatively simple idea. Of course, I gotta show it's a simple implementation. You can write this in a couple of lines of Prolog. You take a generic coverage algorithm that iterates over all rules, finds an embedding for each non-terminal symbol on the left-hand side, and then calls this criterion. You can use this generic algorithm both for positive test suites and for negative. Right? So we take a rule mutation, we just look at the rule and backtrack over all possible mutants of that rule. And by embedding that into the derivation for its left-hand side and then grounding out with, say, the minimal yield, we get a negative test case. Right? This is a new ideas paper. We have done some experimental evaluation. It's a very small font-sized table. Let me just give you the highlight. The number of token mutations grows very large, right? Basically, we can apply four operations at each position, but each of these operations can potentially work with any token. So it grows basically quadratically, right? Rule mutation grows much slower. The number of rule test cases is 1 to 2 orders of magnitude smaller than the number of token mutations. And the two cover different parts of the error space. For our grammar, it's very simple. For instance, just simply arithmetic expressions. The rule mutations and the token mutations are pretty much the same. The overlap between both sets is 96%. So there's very little that's only produced by mutating a token in a positive set or by mutating one of the rules. But if the grammar becomes a bit bigger, we see that the overlap drops down to 60 to 80%, which means that both of them look at different kinds of errors. We can also see that this doesn't take too long. It scales more or less to production grammars. Here is, for instance, modular 2, which has close to 400 rules, right? And it takes a couple of minutes to generate this at the worst case. Right, so 3 minutes for the rule mutation. Qualitatively, we've used this for fault localization. It was very useful finding errors in student grammars and find differences in different versions of Pascal grammars. If you've seen Mokatzi's presentation in the morning, you noticed that only the introduction of negative test cases allowed us to really pinpoint the errors. So, what are the take-home messages? I think negative test cases can be generated constructively. We don't have to rely on an early parser from the golden grammar to figure out whether something is failing or not. We can constructively generate failing test cases. Early testing is better than early parsing, right? The number of edit-based, token-based mutants becomes too large, especially if your positive base test suite is already very large. The number of rule-based mutants remains very reasonable. We've applied this in fault localization. Now, this is a new idea. Where do we want to go with this? We want to define more complicated mutant operations. Talk to me afterwards. We want to use this for grammar repair and also for grammar comparison. If you want to see a demo, find me somewhere. I'm happy to show this. Thanks.
Thank you very much. Right, do we have some questions? I'm scanning.
So is it in a state that I can use this in my compiler's course, so I can take what I think is my solution grammar and generate negative test cases?
It is in a state that I have used it in my compiler course and have taken my golden grammar and generated negative test cases. Now, funnily enough, the golden grammar was broken.
Yeah, I was just thinking.
Yes. Now, so it's a prologue. It's a prologue system. You're welcome to use it. Feel free, but hey, it's researchware. But it's implemented.
It's very cool.
Anybody else? Sure.
So if you have a small student grammar of, I don't know, 20 non-terminals or 10 non-terminals, how can you relate how many test cases do you get?
I can show you how many I got on that example. Those were student grammars, right? I just lost the display, okay. So these are student grammars. These are actually the instructor's golden versions. So we have, 50 non-terminals, 100 rules. We get on the order of 10,000 mutants by mutating the rules, and 30 to 100,000, depending on the size of the positive test case. So you get large numbers, but it's fully automatic, so it's manageable. File I/O is a limiting factor.
solution guarantees this?
It doesn't. But so what I'm doing is I'm generating a well-defined error by, for instance, mutating a rule. So I know what mutation was, right? So I can track that kind of information, but there's no guarantee that a different mutation doesn't generate the same error. But if I key sort my outputs by the generated tokens or by the generated programs, then I know for each program, for each test case, which set of possible mutations was applied. So I'm not going down to a single, but I'm going down to well-defined errors. Yeah.
Just one more question. So, I guess, there must be erroneous test cases that are erroneous that your grammar can, or that your technique cannot generate.
Yes.
So do you have some idea of what kind of things you cannot generate?
Yes, for instance, if you look at simple, like Van Dyke grammars, right? Because of the very limited number of tokens, this follow precede set constraint doesn't work that well. So you can use counting arguments. If you know that open bracket and close bracket are always occurring in pairs in every rule, then you can delete either the open bracket or the closed bracket, even if they don't satisfy the conditions that I've put out there, right? So there's some ideas similar about long distance order. You know that statements have to follow declarations, and there's something in the declaration, the colon, that can't come in the statement. I haven't completely worked that out. But there are some ideas you can generalize this to more complicated conditions.